My name is Sehwan John, and I am a graduate student at MIT working with Drs. Hangbei Kim at the Biomimetic Robotics Laboratory. Today, I'm presenting my work on a slip-based heuristic controller for quadrupedal landing. As an introduction, while many legged robots have been shown to be capable of very dynamic movements like backflipping and jumping and running, there's been less work done on studying how quadrupeds or how robots in general can successfully land and safely recover from highly dynamic conditions. So these high impact events and interactions with the environment would obviously, being able to control these would extend the capabilities of robots to be able to do things such as deploy from unknown conditions or be able to recover safely from accidental pushes and falls in a better way. So this work presents a very simple heuristic controller to absorb the impact of landing and recover thereafter. Some key challenges to note are listed as follows. The controller bandwidth needs to be very high for any kind of landing controller because fall durations can be very short. It's important to have accurate and good state estimation because the Cheetah needs, or the robot needs to have some good sense of how high it is and how fast it's falling or how fast it's falling in any direction to be able to land successfully. It's also important to note that the orientation while falling cannot be adjusted significantly because the limbs of the Cheetah are so light, it's difficult for it to adjust its orientation to be able to land it in a more advantageous way. And lastly, it's unclear what performance metrics define the optimal landing, whether it's some sort of minimization of the ground reaction forces, the acceleration, or jerk, or some other quantity that may be a sum or some combination of those. So with those challenges in mind, we approach the formulation of this quadrupedal landing. We say that when the robot is falling, we have some state of the robot with some falling velocity, with some orientation, with some angular velocity. We make the argument that because the robot obeys ballistic mechanics, we can approximate the floating base touchdown state of the robot. Right before the robot hits the ground, we can approximately know, using ballistic mechanics, what the robot's position, orientation, velocity, and angular velocities are, right at touchdown. So as shown in figure 1, assuming we know those quantities, we approximate the robot to be a slip model. We approximate that it has some sort of single mass and it has some velocity of that mass approaching down. And we can orient the legs in the direction of the velocity to oppose its velocity and negate it as soon as possible. We can set a spring constant K so that this mass never touches the ground and never goes through the ground. We simply need to set K to be large enough. And we have some nominal leg length L, where we outstretch the legs enough so that it has that distance to be able to compress before it returns to a nominal state. Now, this controller relies on detecting contact probabilistically, as was presented in 1 with Gerardo's work, and also it requires feeding the forces into a whole body controller to be able to more accurately determine the torques and stabilize the robot after it's been compressed, and that work is presented in 2 with Donghyun's work on highly dynamic quadrupedal locomotion with whole body impulse control. So figure 2 shows a control scheme for how this algorithm works together, and the results are shown as follows. In simulation with the Unity engine, the quadruped is able to successfully recover from heights of up to 3.5 meters and forward and backwards velocities of around 4 meters a second and lateral velocities of 3.5 meters a second. We also introduced roll and pitch offsets of about 45 degrees and 30 degrees respectively to be able to see how the Cheetah can respond to sequential contacts, even though it's been approximated as a slip model, and we find that it performs relatively well. We also introduced some amount of small angular velocities to all 3 axes, but we find that it handles those cases much worse, and it's much more sensitive to angular velocities in the roll and the pitch direction. This plot of figure 3 demonstrates what we consider a standard jump, which is where the Cheetah is initialized in the air and it has some initial forward velocity and some initial upwards velocity. So it follows a parabolic arc into the ground. Following this solid blue line, which is the Z position of the robot, we see that it jumps, it moves all the way up, follows this arc, and then when it touches the ground, it seems to obey some kind of damped spring motion, which is somewhat close to what we expect because we enforce a slip model. But more importantly, we see that it can stabilize itself before it hits the ground and indeed dampen out and return to some nominal resting state. Now, videos of the simulation were also captured, which can be seen here. So this is simply for a falling condition, straight down, no pitch or roll offsets. This is with a significant offset in pitch, and we see that similar to like how a cat might land, it touches down with the front feet first, absorbs that impact, and then recovers with his back feet to stabilize itself. So let's just play that one more time, like so. The red arrows indicate the direction of the force, and this simulation was done in Unity, as was said before. This is with significant yaw, where we send the cheetah upwards and with a high angular velocity in the yaw direction. And we see that even, at least for this direction, it seems to recover very well. For roll and pitch, it's much more sensitive and fails much more often. And this is what we consider just almost a randomized jump, where we send it sideways at some initial pitch and roll velocity. Relatively small, but we still see that it recovers fairly well. So these values presented here are the limits where it begins to fail, but we haven't fully investigated what combination and in what configurations does the robot really begin to break down, where this controller starts to stop working. So to discuss the results of these, while it shows surprising robustness with this very simple, admittedly very simple open loop style heuristic, it's still very susceptible to failing in real world conditions because it requires very accurate estimation of the state, as well as very precise orientation of the legs and of the conditions around it. It's difficult to evaluate how this might perform to robust or to more with introduction of noise or unexpected modeling or conditions. So this is probably an area where we would need to focus on further and improving the robustness of this controller outside of just the simulation environment. It's also important to note that the force profile was controlled to be linear because we conditioned it to be a spring, but there's no reason to assume that this is the case. There may be some optimal force profile that is much more advantageous to landing that we have not investigated yet. So finding a more optimal force profile, if one exists, would be a significant improvement on this controller. Perhaps most key is being able to ensure this robustness to real world conditions. And the most difficult part about that is ensuring that we have good state estimation and being able to ensure that the controller is able to stabilize itself. For future work, we're both exploring using a vision system and also integrating a vision system into the mini Cheetah so that it can predict where it is in the environment and see the height, its height offset from the ground more accurately. And also, we're investigating using feasible wrench polytopes to plan for motion and recovery instead of using this very feed-forward open loop style slip controller. We believe that with feasible wrenches, it'll be more direct correlation to tell between the current velocity and acceleration of the robot to where it should actually be in a region where it can be stabilized. Thank you so much, and please let me know or reach out if you have any questions. And that has been my presentation. I hope you enjoyed it.